Welcome curious minds and sleepy thinkers. You've found a soft place to land, a quiet corner of the universe where the whispers of possibility can drift through your mind, gentle as stardust. Tonight we're going to tiptoe into one of the most profound and mysterious questions humanity has ever dared to ask. Could we as a species truly make a home on another world, far beyond our familiar blue sphere? Could Mars, that distant reddish jewel in our night sky, become a second cradle for human civilization? But don't worry, we'll take it slow. This isn't a race through equations or a frantic dash across the cosmos. It's more like floating through a galaxy of ideas with a cup of chamomile tea in hand, allowing each thought to gently unfold like a cosmic flower, blooming in the silent vastness. For millennia, the very existence of those luminous points of light scattered across the velvety canvas of the night sky has stirred something deep within the human spirit. Long before we understood the intricate dances of celestial mechanics, before we even conceived of planets as worlds, these wandering stars held a special, almost sacred significance. Mars, with its distinct ruddy glow, often stood out a fiery ember among the colder, more distant lights. Ancient civilizations wove elaborate myths around it, attributing its martial hue to gods of war, of passion, of relentless energy. This early symbolic connection laid the groundwork for a fascination that would only deepen with time, hinting at a profound, almost innate human desire to not just observe, but to understand, to name, and ultimately, to reach out and touch the cosmos. It's as if inscribed within our very being is a quiet, persistent curiosity about what lies beyond our immediate horizon. As human knowledge blossomed and our instruments grew sharper, the character of this fascination began to shift. The telescope, that wondrous eye into the heavens, transformed Mars from a mere point of light into a discernible sphere, hinting at features, contours, and a distinct personality. This newfound clarity didn't diminish the mystery, it only deepened, it adding layers of scientific intrigue to the ancient myths. The very idea of canals on Mars, first observed or perhaps imagined through early telescopes in the 19th century, ignited a wildfire of speculation. Were these the remnants of ancient waterways engineered by a long-lost civilization? Was Mars a dying world, its inhabitants desperately trying to preserve their vital resources? These questions weren't merely scientific queries. They were deeply empathetic projections of our own struggles and triumphs onto a distant stage. We yearned for company in the vast silence, for evidence that life intelligent and striving could emerge elsewhere in the universe. This period marked a crucial transition from mythical interpretations to speculative science, though the lines between the two often blurred delightfully. The sheer human impulse to find kinship, to imagine other beings grappling with challenges akin to our own, speaks volumes about our inherent desire for connection across the cosmic expanse. Indeed, this pervasive interest found its way into the fabric of everyday life, seeping into the public consciousness with remarkable ease. A glance through historical archives reveals that discussions about Martian life were not confined to academic journals or hushed scientific gatherings. Imagine picking up your morning paper in 1911, perhaps the New York Times, and finding an entire article dedicated to the subject of life on Mars, complete with earnest debates and bold pronouncements. This wasn't just a quirky sidebar. It reflected a widespread cultural phenomenon, a shared dream that permeated society from the highly educated to the most ordinary citizen. The concept of Martian inhabitants, whether advanced engineers or simple struggling beings, became a comforting thought, a quiet hum in the collective mind, reassuring us that we might not be utterly alone in this vast, silent universe. It was a beautiful symphony of hope and speculation, playing out across dinner tables and in intellectual salons, nurturing the seed of curiosity that would eventually blossom into our current, more grounded ambitions. Yet, as we gently probe this historical fascination, we arrive at a fascinating contemporary shift. The whispers of ancient civilizations and bustling Martian cities have given way to something far more tangible, more immediate. The modern scientific community, bolstered by decades of robotic exploration and refined analytical tools, is now revisiting the question of life on Mars with renewed vigor and unprecedented precision. And remarkably, the sentiment has swung back towards optimism. Even institutions as rigorously scientific as NASA now genuinely believe there is something profound to be found there. This isn't the romanticized musing of a century ago. This is a calculated, data-driven conviction. The primary objective of the Perseverance rover, that marvel of modern engineering, launched recently, is not merely to study Martian geology or atmospheric conditions, but to actively seek out evidence of past or even present biological life. It's a seismic shift from passive observation to active investigation, armed with sophisticated instruments designed to detect the faint, elusive chemical signatures of life itself. This focus on biological signatures represents a significant departure from many previous missions. Apart from the pioneering Viking program in the 1970s, which carried rudimentary life detection experiments, most other Martian endeavors were primarily focused on the past prospects of habitability. In simpler terms, they were looking for signs that Mars could have supported life, rather than direct evidence that it did. They meticulously searched for the ghostly traces of ancient liquid oceans, for geological formations indicative of flowing water, for environments that might have once been welcoming to microbial existence. These were crucial foundational steps, akin to searching for the ruins of an ancient city to determine if anyone ever lived there. But now with Perseverance, we're sending a highly specialized detective equipped to find not just the empty houses, but perhaps the fossilized remnants of the occupants themselves. This methodical, patient approach, buildings layer upon layer of knowledge, has been laying the indispensable groundwork for the even grander ambitions that are now taking shape. Every data point, every image, every chemical analysis is a meticulously placed brick in the foundation of humanity's audacious dream. Indeed, with this ever-deepening understanding and the tangible evidence of Mars's past aqueous environments, the conversation has soared beyond mere scientific inquiry. We are now daring to ask, can we as a species colonize Mars? And if so, how would we embark upon such an unprecedented journey? This is no longer a rhetorical question reserved for the pages of speculative fiction. Numerous space agencies across the globe, and perhaps even more strikingly private companies born from the fertile ground of innovation and ambition, now have their sights firmly set on putting colonies on Mars. Names like the Mars Society and Mars One, once sounding almost fantastical, have become tangible entities rallying support and resources, transforming a lofty aspiration into a strategic, long-term objective. This burgeoning interest, this shared drive to push beyond Earth's comfortable embrace, is understandable. Our neighboring planet, despite its harshness, possesses a series of intriguing characteristics that make it uniquely similar to our homeworld, beckoning us with the tantalizing promise of a second chance, a cosmic fresh start. This shared fascination is not without reason. Imagine for a moment the vast cosmic ocean teeming with countless celestial bodies. Among them, Mars stands out as the closest celestial body where life could have existed in the past, making it an irresistibly alluring target for our ongoing quest to understand the universe and our place within it. It whispers tales of a warmer, wetter, past a time when liquid water might have flowed freely across its surface, perhaps nurturing the very seeds of life. This historical echo, combined with its relative proximity compared to other potentially habitable worlds, paints Mars as the most viable stepping stone for humanity's expansion beyond Earth. It's like finding a slightly less hostile island in a vast, unpredictable sea, offering a glimmer of hope for future voyages. However, as with any grand voyage into the unknown, the path to Mars is not merely a straight line of technological triumph. It is a nuanced journey filled with profound challenges that demand our deepest ingenuity and our most tenacious resolve. The first and perhaps most immediate question for any aspiring Martian settler is deceptively simple. How would colonists even get there? And once they arrived, how would they survive the trip itself? While sounding manageable at about 3 months under the most optimal launch conditions, a cosmic alignment that happens only every 26 months, akin to catching a rare fleeting celestial bus, conceals a host of formidable dangers. On the surface, 3 months might seem like a long voyage on a cruise ship, perhaps a little more cramped, a little less luxurious, but conceptually similar. Yet this analogy dramatically understates the profound and relentless perils of deep space. The true gravity of the journey lies not merely in its duration, but in what those 3 months truly entail. For the entirety of that journey, you would be spending your time outside the comforting embrace of Earth's magnetic field, our planet's invisible shimmering shield that deflects the harshest cosmic elements. Out here in the cold, silent void, you are relentlessly exposed to the solar wind and cosmic radiation, two invisible yet incredibly potent adversaries. Imagine being adrift in an open boat during a perpetual storm, but instead of waves, you're constantly buffeted by invisible particles traveling at immense speeds, each one carrying the potential to inflict lasting damage. Prolonged exposure to this relentless barrage of radiation is not merely uncomfortable, it can be devastating. It's known to cause astronauts to develop serious health issues, including various forms of cancer, and even disturbingly, symptoms akin to Alzheimer's disease, long before they ever set foot on the Martian surface. The very act of traveling through space becomes a silent, insidious battle for the human body, a profound challenge to our biological resilience. Fortunately, the human spirit, ever resourceful, is already contemplating ingenious ways to mitigate these unseen dangers. One promising line of thought involves shielding the astronauts using materials specifically chosen for their ability to absorb and deflect radiation. Imagine the spaceship's construction not just as a hull designed for structural integrity, but as a protective cocoon rich in hydrogen-based materials. Hydrogen, with its single proton, is remarkably effective at scattering and slowing down high-energy particles. Going a step further, some proposals even envision the cabin itself being surrounded by a water tank integrated into the walls. Water, being famously rich in hydrogen, transforms from a mere life-sustaining fluid into a liquid shield, an elegant and practical solution that leverages a vital resource for dual purposes. Picture your living quarters nestled within a liquid barrier, a clear, shimmering defense against the invisible storm outside. Another, perhaps more ambitious option to counter the relentless onslaught of cosmic radiation involves creating a magnetic field around the spacecraft. This concept, drawing inspiration from Earth's own protective magnetosphere, would essentially generate a miniature artificial bubble of safety around the entire vessel, deflecting the charged particles, much like our planet does. However, this magnificent idea comes with a colossal caveat. It requires generating a truly enormous amount of energy from a reactor small enough to comfortably fit on a spacecraft. And here we confront a current frontier of our technological capabilities. We simply don't have the technology to safely miniaturize such a powerful reactor just yet. It's like dreaming of a magic cloak that makes you invisible, but realizing you first need to invent the loom and the thread from scratch. It's a distant yet tantalizing possibility, pushing the boundaries of what we deem achievable in the realm of power generation and spacecraft design. The sheer scale of the energy required is a humbling reminder of the vast chasm between current technological prowess and future aspirations. Beyond the immediate physical dangers, the sheer distance to Mars introduces another more subtle, yet profoundly impactful challenge: the ever-increasing time delay with communications. On Earth, we live in a world of near-instantaneous global connection. If you phone someone on the other side of the planet, the time delay is negligible, perhaps a split second barely noticeable. We take this fluidity of communication for granted, a continuous, seamless flow of information that underpins our modern lives. At these terrestrial distances, the speed of light, while astronomically fast, feels effectively instantaneous. However, when we venture into the astronomical distances of interplanetary travel, the speed of light, that ultimate cosmic messenger, begins to feel remarkably slow. Imagine trying to have a conversation where every word takes minutes to travel, minutes to be heard, and minutes more for a reply to come back. On Mars itself, the fluctuating distance to Earth means that transmissions will be delayed by anything between a frustrating 3 to a staggering 22 minutes. And remember, this is only one way. So if a Martian settler sends a message accounting for the return transmission, the minimum delay for a complete exchange, a single question and answer, is a daunting 6 minutes. This makes a normal fluid phone conversation utterly impractical, transforming what we perceive as a simple back and forth into a disjointed, agonizingly slow process. While text, audio, and video messages are still entirely possible, albeit with these frustrating delays, the implications for critical situations are profound. Martian settlers will have to be incredibly self-reliant, prepared to fend for themselves, and make immediate decisions in cases of emergencies or equipment failures. The very notion of real-time remote operations or immediate assistance from Earth becomes unfeasible, highlighting a profound sense of isolation that will define their daily existence. It's like cutting the umbilical cord, not just physically, but in the very flow of information, forcing a newfound independence that is both liberating and terrifying. Now let us gently drift deeper into our cosmic reverie, allowing our thoughts to settle on the pioneering spirit that has already touched the dusty plains of Mars. Long before human footsteps could ever hope to grace its rusty surface, our robotic proxies, tireless and brave, have been whispering secrets back to us across the vast cosmic ocean. These aren't just machines. They are our extended senses, our metallic eyes and hands patiently gathering clues about a world that has captivated us for so long. Consider the legendary Curiosity and Opportunity rovers, two names that echo with tales of endurance and discovery. Opportunity, the plucky geologist, was initially designed for a mere 90 Martian days, a fleeting visit. Yet it persevered for over 15 years, traversing over 45 kilometers, a marathon, across an alien desert, powered primarily by the sun. Imagine that, 15 years of quiet, steady exploration, sending back images of ancient streambeds and mineralogical evidence of past water. It was like a diligent cartographer, slowly, meticulously mapping a lost continent. Each rotation of its wheels, a gentle whisper of new knowledge. Its solar panels, though occasionally dusted by Martian winds, were its lifeblood, absorbing the faint sunlight and converting it into the energy that kept its scientific heart beating. When the massive dust storm of 2018 finally engulfed the planet, blotting out the sun and shrouding Opportunity in perpetual darkness, it was a poignant moment, like saying goodbye to an old beloved friend who had served beyond all expectations. Its silence was a testament to its extraordinary journey, a small metallic monument to perseverance. And then there was Curiosity, the larger, more sophisticated laboratory on wheels still active today, patiently probing the ancient layers of Gale Crater. This rover isn't just taking pictures. It's drilling into rocks, analyzing soil samples with a suite of advanced instruments, diligently searching for signs that Mars could once have supported microbial life. It's like a quiet scholar meticulously poring over ancient texts, deciphering the subtle clues left behind by a vanished epoch, sifting through the dust and stones for the faint echoes of biological processes that might have played out billions of years ago. Each rock it touches, each scoop of soil it analyzes, is a page in Mars's autobiography slowly being revealed to us. The data they have collectively gathered, the intricate images they've captured, and the profound scientific insights they've offered have done more than just fill scientific databases. They have ignited a collective interest, a rekindled spark in the human heart about the future prospects of Mars. They showed us that the red planet is not merely a barren wasteland, but a world with a complex past, a potential history that echoes with the tantalizing possibility of life, even if only fleetingly, in the distant past. These robotic explorers are not just our eyes. They are our silent storytellers preparing the narrative for the human chapters yet to be written. Their quiet, tireless work is the very foundation upon which our grandest Martian dreams are built. This growing scientific understanding, combined with the sheer audacity of the Martian dream, has fostered a remarkable phenomenon: the rise of private companies and nonprofit organizations dedicated to promoting its colonization. It's no longer solely the domain of massive government agencies with decades-long plans and intricate political processes. Now, alongside the steady, methodical work of NASA and ESA, you find the vibrant, often audacious energy of private entities. Think of organizations like the Mars Society, founded on the principle that humans must go to Mars, driven by an unshakable belief in humanity's destiny as a multiplanetary species. They advocate, educate, and even conduct analog missions on Earth, simulating Martian living conditions to test technologies and train future explorers. They are the passionate evangelists, fanning the flames of public imagination and pushing the boundaries of what is considered achievable. Then there were initiatives like Mars One, which, while ultimately unsuccessful in its ambitious goal of a one-way trip, captured the world's attention with its sheer audacity, proving just how deeply the idea of settling Mars resonated with millions of hopeful volunteers. These private ventures operate with a different rhythm, often unburdened by the bureaucratic layers of government programs, allowing for quicker decision-making and a more aggressive pursuit of goals. They bring a unique blend of entrepreneurial spirit, cutting-edge technology, and sometimes a dash of audacious showmanship. Their motivation isn't solely scientific discovery, though. That is often a component. It's about pushing the boundaries of human achievement, about creating new economies, about expanding the very definition of civilization. They see Mars not just as a laboratory, but as a new continent waiting to be settled, a blank slate for human ingenuity and resilience. This infusion of private capital and innovative thinking has dramatically accelerated the conversation, transforming it from a distant aspiration into a more immediate, almost palpable goal. It's like a vibrant ecosystem forming around the idea of Mars, with different entities playing different roles, all contributing to the momentum towards that distant red horizon. The sheer diversity of approaches from nonprofit advocacy to billion-dollar space ventures highlights the multifaceted nature of this grand human endeavor, proving that the fascination with Mars is as broad as it is deep, touching hearts and minds across the spectrum of human ambition. This modern surge of interest in Mars, both scientific and entrepreneurial, is not a sudden new phenomenon. It has deep roots in a long and captivating history of human speculation about life beyond Earth. The notion of life on Mars in some form has been around since as early as the 19th century, a time when telescopes were rapidly improving, revealing more details of our celestial neighbors. Astronomers peering through their lenses began to observe faint linear markings on the Martian surface. In the absence of high-resolution images, and fueled by a fervent imagination, many interpreted these as canals, artificially constructed waterways, perhaps built by an intelligent Martian civilization struggling to channel dwindling water resources across their drying planet. This wasn't a crazy assumption, considering the limitations of the technologies they had at the time. Their instruments were good enough to hint at structure, but not quite sharp enough to fully resolve the true natural complexities of the Martian terrain. It was a leap of faith, a hopeful interpretation of ambiguous data, reflecting a universal human tendency to see patterns and purpose even where none might exist. Think of it as a beautiful collective dream, shared by an entire generation. A newspaper article from the New York Times in 1911, an artifact from a bygone era, even spent time discussing this very subject, underscoring just how deeply this notion had permeated the public consciousness. It wasn't just confined to the scientific elite. It was a topic of conversation in parlors and pubs, sparking debates and fueling popular novels and stories. This rich tapestry of speculation, though scientifically disproven by later clearer observations, served an invaluable purpose. It kept the flame of curiosity alive, nurturing a profound wonder about other worlds, and subtly preparing humanity for the revelations that would inevitably follow. The fictional Martians, whether benevolent or menacing, paved the way for the real Mars, making it a place of intrigue and possibility, rather than just another cold, distant rock. These early narratives, however imaginative, laid the crucial psychological and cultural groundwork for the bold ambitions we harbor today, proving that sometimes even our wildest dreams can lead us closer to the truth. However, after a period where the scientific consensus leaned towards a barren, lifeless Mars, the idea of life on Mars is now remarkably gaining more proponents again. This isn't the romanticized, speculative hope of the 19th century. It's a sober, evidence-based resurgence, driven by the remarkable discoveries of our robotic explorers. Even NASA, an organization characterized by its scientific rigor and cautious pronouncements, openly acknowledges that there is something profound to be found there. This renewed optimism stems from a deeper understanding of Mars's geological history, particularly the compelling evidence for vast amounts of past liquid water on its surface, as well as the presence of key chemical building blocks essential for life. It's like finding an ancient, long-abandoned house that shows clear signs of once being a vibrant home. The main objective of the Perseverance rover, which majestically launched and landed in recent years, is precisely this: to actively find direct evidence of life, specifically microbial life that may have once thrived there. This mission marks a crucial shift in our investigative approach. Apart from the pioneering Viking program in the 1970s, which had some limited biological experiments, most other Martian missions were designed with a different focus. They didn't have the specific means of searching for biological life itself. Rather, their primary goal was to investigate the past prospects of habitability on Mars. In other words, they were searching for signs of past liquid oceans, for riverbeds and lakebeds for minerals that only form in the presence of water. They were looking for the conditions conducive to life, not for direct evidence of the microbes themselves. It was like searching for an empty cradle, hoping to deduce if a baby had ever slept there. These missions, with their focus on water and geochemistry, were absolutely vital. They were meticulously laying the foundation for what is coming up, creating a comprehensive picture of Mars's environmental evolution. They taught us where to look, what to look for, and how the planet changed over billions of years. Now, with Perseverance, we are graduating to a more direct, more ambitious search, aiming to uncover the tangible, if microscopic, remnants of life itself. This represents the cutting edge of astrobiology, a silent, methodical hunt for answers to one of humanity's most profound questions: are we alone? The very instruments on board Perseverance are designed to be exquisitely sensitive, capable of detecting the faint chemical whispers of ancient life, pushing the boundaries of what our technology can achieve in the search for our cosmic neighbors. The cumulative effect of these decades of tireless exploration, the meticulous gathering of data, and the ever-refining scientific hypotheses has led us to this exciting juncture. The ground has been thoroughly prepared, the scientific questions sharpened, and the technological capabilities are reaching an unprecedented level of sophistication. This is why numerous space agencies and private companies now have their eyes firmly set on putting colonies on Mars. The dream, once ethereal, is slowly solidifying into a concrete plan, albeit one fraught with immense complexities. But before we can even begin to imagine structures rising from the Martian soil or crops growing under artificial suns, we must first confront the most fundamental and daunting questions. How would colonists even get there? And once they arrived, how would they survive the utterly alien environment? These are the initial crucial gates we must pass through on our journey to becoming a multi-planetary species. The journey itself, the cosmic road trip to Mars, is a significant undertaking. With the most optimal launch conditions, which occur only every 26 months when Earth and Mars align favorably, the trip would take about 3 months. On the surface, this doesn't seem excessively long. In our modern world, a 3-month voyage might evoke images of a long cruise ship journey, perhaps a little more cramped and less luxurious, but conceptually similar. Yet this analogy drastically understates the profound and relentless perils of deep space. For the entirety of those 3 months, you would be spending your time outside the comforting, life-giving embrace of Earth's magnetic field. Our home planet possesses an invisible shimmering shield, a vast magnetic bubble that deflects the harshest cosmic elements, protecting all life within. But once you venture beyond this ethereal protection, you are plunged into an environment of unrelenting exposure to the solar wind and cosmic radiation, two invisible yet incredibly potent adversaries. Imagine being adrift in an open boat during a perpetual silent storm, where instead of visible waves, you're constantly buffeted by invisible particles, traveling at immense speeds, each one carrying the potential to inflict lasting damage at a cellular level. This relentless barrage of radiation, composed of high-energy particles flung from the sun during solar flares and galactic cosmic rays from distant supernovae, is not merely uncomfortable. It can be devastating for the human body. Prolonged exposure to this kind of radiation is known to cause astronauts to develop a variety of serious health issues. These include an increased risk of various forms of cancer, as the radiation can damage DNA and lead to uncontrolled cell growth. Even more disturbingly, studies suggest a potential link to cognitive impairments, with some research indicating that long-term exposure could even contribute to symptoms akin to Alzheimer's disease, long before the astronauts ever set foot on the Martian surface. The very act of traveling through space becomes a silent, insidious battle for the human body, a profound challenge to our biological resilience that begins the moment the spacecraft leaves Earth's protective cocoon. It's a stark reminder that even the void of space carries hidden dangers, unseen threats that underscore the incredible bravery of those who would undertake such a voyage. Fortunately, the human spirit, ever resourceful, is already contemplating ingenious ways to mitigate these unseen dangers, to weave a protective cloak around our brave travelers. One promising line of thought involves shielding the astronauts using materials in the ship's construction that are rich in hydrogen. Hydrogen, with its single proton, is remarkably effective at scattering and slowing down high-energy particles, acting like a cosmic cushion to absorb the impact of the radiation. Imagine the spaceship's hull not just as a structural shell, but as a multi-layered shield meticulously crafted with materials designed to deflect and dissipate these harmful rays. Going a step further, some brilliant proposals even envision the cabin itself being surrounded by a water tank integrated into the walls. Water, being famously rich in hydrogen, H2O, transforms from a mere life-sustaining fluid into a liquid shield, an elegant and practical solution that leverages a vital resource for dual purposes, sustaining life and protecting it. Picture your living quarters nestled within a shimmering clear liquid barrier, a dynamic defense against the invisible storm raging outside, transforming a necessity into an innovative protective measure. This elegant simplicity, using what we have in abundance for multiple purposes, is a hallmark of truly clever engineering. Another, perhaps more ambitious option to counter the relentless onslaught of cosmic radiation involves creating an artificial magnetic field around the spacecraft. This concept, drawing profound inspiration from Earth's own magnificent invisible shield, its magnetosphere, would essentially generate a miniature contained bubble of safety around the entire vessel. This artificial magnetic field would then deflect the charged particles of solar wind and cosmic rays, much like our planet does on a grand scale, guiding them harmlessly around the spacecraft. However, this magnificent idea comes with a colossal caveat. It requires generating a truly enormous amount of energy, and crucially doing so from a reactor small enough to comfortably fit on a spacecraft. And here, we confront a current frontier of our technological capabilities. We simply don't have the technology to safely miniaturize such a powerful nuclear reactor to the necessary scale or to contain its energy output for sustained periods just yet. It's like dreaming of a magic cloak that makes you invisible, but realizing you first need to invent the loom and the thread from scratch, along with the very fabric of magic itself. It's a distant yet tantalizing possibility, pushing the very boundaries of what we deem achievable in the realm of power generation and spacecraft design. The sheer scale of the energy required is a humbling reminder of the vast chasm between current technological prowess and future aspirations, illustrating that some of the greatest challenges lie not in the destination, but in the journey itself and how we choose to protect those who embark upon it. Beyond the immediate physical dangers of radiation and the engineering feats required for shielding the sheer distance to Mars introduces another more subtle yet profoundly impactful challenge: the ever-increasing time delay with communications. On Earth, we live in a world of near instantaneous global connection. If you phone someone on the other side of the planet, the time delay is negligible, perhaps a split second, barely noticeable, a mere blink in the grand scheme of conversation. We take this fluidity of communication for granted, this continuous, seamless flow of information that underpins our modern lives, from urgent medical consultations to casual chats with loved ones. At these terrestrial distances, the speed of light, while astronomically fast, approximately 300,000 kilometers per second, feels effectively instantaneous, binding us all together in a single synchronous pulse. However, when we venture into the astronomical distances of interplanetary travel, particularly to a world as far as Mars, the speed of light, that ultimate cosmic messenger, begins to feel remarkably frustratingly slow. Imagine trying to have a conversation where every single word takes minutes to travel, minutes to be heard, and minutes more for a reply to come back. It transforms the very nature of interaction. On Mars itself, the fluctuating distance to Earth, due to the elliptical orbits of both planets, means that transmissions will be delayed by anything between a relatively short 3 minutes to a staggering 22 minutes. And remember, this is only a one-way delay. So if a Martian settler sends a message accounting for the return transmission, the minimum delay for a complete exchange, or a single question and its corresponding answer, is a daunting 6 minutes. This makes a normal fluid phone conversation utterly impractical, rendering it into a disjointed, agonizingly slow process, more akin to sending letters by very slow post. While text, audio, and even pre-recorded video messages are still entirely possible, albeit with these frustrating conversation-killing delays, the implications for critical situations are profound and immediate. Martian settlers will have to be incredibly self-reliant, prepared to fend for themselves and make immediate life-or-death decisions in cases of emergencies, equipment failures, or unforeseen circumstances. The very notion of real-time remote operations or immediate guiding assistance from Earth becomes utterly unfeasible, highlighting a profound sense of isolation that will define their daily existence. It's like severing the umbilical cord, not just physically, but in the very flow of information, forcing a newfound independence that is both liberating in its autonomy and terrifying in its absolute responsibility. This forced self-sufficiency, born from the vastness of space and the immutable laws of physics, becomes a defining characteristic of Martian life, a constant reminder of their pioneering solitude. Beyond the stark physical and communicative hurdles lies a more subtle, yet equally formidable challenge: the psychological demands of a prolonged journey through the void. Imagine being confined to a space no larger than a small apartment with a handful of companions for 3 relentless months. There's no escaping the enclosed environment, no fresh air from an open window, no change of scenery beyond the shifting panorama of stars and the increasingly distant blue marble of Earth. This spatial and sensory deprivation can weigh heavily on the human psyche, fostering feelings of claustrophobia and monotony. The very rhythm of life, so accustomed to the subtle variations of terrestrial days and seasons, would be replaced by the artificial hum of life support and the unchanging vista of deep space. Moreover, the dynamics within the crew become magnified in such a tightly confined setting. Small irritations can fester, minor disagreements can escalate, and the sheer lack of personal space can become a source of profound stress. Each individual's quirks and habits, usually absorbed by the vastness of everyday life on Earth, would become intensely amplified. It's like being trapped in an extremely long road trip, but with no possibility of pulling over, no option to step outside and clear your head. The crew must learn to navigate not just the cosmos, but the complex, intricate cosmos of human personality, developing an extraordinary level of tolerance, communication, and mutual respect. Their collective psychological well-being is as crucial as the integrity of their spacecraft. Adding to this, the profound sense of distance and isolation from Earth would undoubtedly cast a long shadow. Gazing back at our home planet, shrinking into an ever smaller dot of blue and white, would evoke a mix of awe and profound longing. The familiar faces, the comforting sounds, the very scent of Earth's air, all would be impossibly distant, accessible only through delayed messages and fading memories. This emotional detachment, combined with the knowledge of being hurtling through an unforgiving void with no immediate turning back, demands a particular kind of mental fortitude. It's not just about enduring discomfort. It's about processing a deep existential shift in one's place in the universe. The vast, silent emptiness outside the viewport can be both beautiful and profoundly unsettling, a constant reminder of their fragility and remoteness. The psychological burden of knowing that immediate assistance is impossible, that they are truly on their own, far beyond the reach of conventional rescue, creates a unique kind of pressure testing the very limits of human resilience and courage. This emotional landscape is as critical to chart as the physical trajectory to Mars, for without sound minds, even the most robust spacecraft and advanced technologies will falter. The journey is not just a test of engineering, but a profound examination of the human spirit. But let us imagine for a moment that all these formidable difficulties of the journey are somehow overcome. Picture our brave colonists having traversed the vast cosmic sea, their ship, a weary but triumphant vessel, finally drawing near to the tantalizing red orb. They've survived the radiation, navigated the communication delays, and forged bonds stronger than steel in the crucible of their long voyage. Now they stand at the precipice of a new existence, gazing down at their future home. The very first whisper on their minds, echoing the inquiries of explorers throughout history, would undoubtedly be, where would they settle? On Earth, our choices of settlement are dictated by natural resources, climate, and strategic locations. On Mars, these factors take on an entirely new life-or-death significance, making the choice of landing site perhaps one of the most critical decisions of the entire mission. At the moment, there is no single universally agreed-upon favorite candidate for a human settlement. The Martian landscape, beautiful in its desolate grandeur, offers a variety of intriguing possibilities, each with its own unique advantages and daunting drawbacks. One distinct possibility, a location that whispers with the promise of a vital resource, is the North Pole. Much like Earth, Mars possesses polar ice caps, and these aren't just frozen carbon dioxide. Within their vast, layered expanse lies a significant presence of water ice. Imagine a landscape of rolling reddish dunes meeting pristine, ethereal white caps, a stark contrast that holds the key to life. The immediate appeal of the poles is obvious: water in its solid form, readily available for extraction. Water is not just for drinking. It's fundamental for growing food, for producing breathable oxygen through electrolysis, and even for generating rocket fuel by breaking it down into hydrogen and oxygen. Access to this essential commodity without having to drill deep or process complex subsurface materials would be a monumental advantage, simplifying the initial precarious stages of establishing a foothold. However, the poles also present extreme challenges. perpetual cold long periods of darkness during winter, and fierce polar storms that can shroud the landscape in blinding, abrasive dust. It's a trade-off, a quiet negotiation with the planet's harsh realities, abundant water, but at the cost of enduring some of the most unforgiving environmental conditions. Another truly fascinating option, a testament to the unexpected treasures hidden within Mars's scarred surface, is the 81-kilometer-wide Korolev crater. This enormous ancient impact basin isn't just a depression in the Martian crust. It's a colossal natural ice rink, perpetually filled with a thick, gleaming layer of water ice. Picture a vast circular mirror stretching for miles, reflecting the faint Martian sunlight. The reason for this permanent icy lake lies in the crater's unique topography and the Martian atmosphere. While the atmosphere isn't thick enough for liquid water to pool on the surface of Mars for any lengthy period of time, the low pressure causes it to rapidly sublimate, turning directly from ice into vapor. The deep sheltered basin of Korolev crater acts like a natural cold trap. Here, at the bottom of craters, where it is cold enough, pockets of water are locked up in perennial ice, protected from the sun's direct rays and the thin, hungry atmosphere. This makes Korolev crater a particularly attractive site. Its ice is relatively accessible, sitting within a defined geological feature, potentially easier to access and extract than diffused polar ice sheets. It's like finding a massive frozen reservoir, a ready-made source of precious water waiting to be tapped. The beauty of such a site lies in its contained nature, offering a concentrated resource that could become the beating heart of an early Martian colony. Beyond the visible icy expanses, Mars, in its subtle way, holds even more secrets beneath its dusty crust. There is also the distinct possibility of settling near underground water deposits found in permafrost under the Martian crust. Think of it as a vast ancient freezer, holding onto the remnants of a wetter past just beneath the surface. For years, scientists have been meticulously piecing together the subsurface hydrological map of Mars, using the sophisticated eyes and ears of our orbiting spacecraft. Studies based on data from a combination of Mars orbiters, instruments that use radar spectrometers and thermal cameras, have revealed and mapped out numerous locations for water under the ground all across the planet. These findings are like a treasure map indicating hidden veins of ice, protected from the harsh surface conditions by layers of regolith and rock. While more difficult to extract than surface ice, requiring specialized drilling equipment and more energy to reach these underground reservoirs, could open the door to colonies in more equatorial latitudes. This is a truly game-changing prospect. Why? Because equatorial regions on Mars are significantly warmer, receiving much more direct sunlight than the frigid poles or the eternally shaded craters. This seemingly small difference in temperature and light intensity translates into a monumental advantage for solar panels for energy production, which would be much more effective and reliable in these sunnier regions. Imagine the stark contrast, a solar farm at the pole struggling for light during the long winter night, versus one near the equator, bathing in relatively consistent sunlight. This balance, drilling deeper for water but gaining immense benefits in energy production, makes these underground permafrost deposits a compelling target. It shifts the strategic thinking from simply chasing the most accessible water to finding the optimal balance of resources and environmental conditions. It's about leveraging the planet's hidden bounty to unlock warmer, more energy-rich locations, truly expanding the possibilities for where humanity could lay down its roots. Mission planners, with their meticulous calculations and long-term vision, would probably try to combine this finding of subsurface water with another crucial consideration: ground elevation. This is where the landscape of Mars reveals its subtle complexities, offering strategic advantages that are not immediately obvious. The northern hemisphere of Mars, generally speaking, has a much lower ground elevation compared to the rugged, heavily cratered southern highlands. This lower elevation means that the atmosphere is thicker there. While thicker on Mars still means incredibly thin by Earth standards, perhaps less than 1% of Earth's atmospheric pressure. This subtle difference is absolutely critical for the delicate dance of landing a spacecraft. Imagine trying to slow down a massive speeding object from hundreds of thousands of miles an hour. On Earth, our thick atmosphere acts as a natural brake, generating significant drag that helps slow down spacecraft during atmospheric entry, allowing parachutes to deploy effectively and heat shields to shed their energy. On Mars, with its whisper-thin atmosphere, every bit of atmospheric drag is precious. A thicker atmosphere in the northern lowlands translates to greater aerodynamic braking, making it perfect for slowing and landing a spacecraft more safely and efficiently. It's like having a slightly thicker cushion to land on, reducing the stress on the vehicle and the precision required for a soft touchdown. So combining a location with abundant subsurface water in the warmer equatorial zones with a region of lower elevation in the northern hemisphere becomes a kind of optimal blend, a sweet spot where resource availability meets engineering feasibility, laying the groundwork for a safer and more sustainable initial settlement. Beyond the essential need for water and a safe landing zone, another fascinating consideration when looking for a settlement location on Mars is to see if there are lava tubes nearby. A lava tube is basically a long naturally formed cave that formed when molten magma flowed through it, much like a subterranean river. Over time, the magma drained away, leaving behind a hollow, fairly uniform tunnel. We see many examples of these on Earth, often explored by cavers and scientists revealing hidden subterranean worlds. On Mars, the volcanic history suggests that these tubes could be incredibly vast, perhaps even large enough to house entire buildings inside. Imagine a natural pre-built shelter already excavated and protected by miles of solid rock. These subterranean tunnels offer incredible advantages for early Martian settlers. Firstly, they provide natural shielding from the harsh Martian surface environment. The layers of rock above a lava tube would offer excellent protection from the relentless cosmic radiation, which is a major concern on Mars, due as it lacks a global magnetic field. It's like having a natural lead blanket wrapped around your living quarters, a thick, impenetrable barrier against the invisible storm from space. Secondly, these tubes would offer protection from micrometeorite impacts. The Martian surface is constantly bombarded by tiny space rocks, which, while often small, can cause significant damage to unshielded habitats. Underground settlers would be safe from these constant random projectiles. Thirdly, lava tubes could provide thermal stability. The ground temperature variations on Mars are extreme, swinging wildly from frigid nights to relatively warmer days. Underground, the temperature tends to be far more stable, creating a more manageable environment for human habitats, requiring less energy for heating and cooling. It's like having a perfectly insulated, naturally climate-controlled environment, a significant relief from the extreme swings on the surface. While lava tubes and caves have indeed been identified on Mars through orbital imaging and geological analysis, the challenge lies in finding suitable candidates. It's not enough for a lava tube to simply exist. A truly viable settlement location would also need to carefully consider what we mentioned before: the elevation of the location for safe landing, and critically, the prospects of nearby water, whether in surface ice or accessible subsurface deposits. A lava tube in a location with high elevation would make landing prohibitively difficult, and a tube far from any water source would negate many of its benefits, forcing settlers to transport vital resources over vast distances. So, the search for the ideal Martian settlement site becomes a complex interplay of multiple factors: geology, atmosphere, resources, and protection. It's like searching for a perfect puzzle piece, one that fits seamlessly into a multi-dimensional puzzle, offering shelter, resources, and accessibility, all in one remarkable package. These hidden tunnels, once the fiery arteries of a young Mars, could become the quiet, protected cradles of humanity's future on the red planet, offering a silent promise of refuge beneath the alien sky. Once a site has been chosen, a painstaking process of analyzing every available piece of data, weighing the pros and cons of water accessibility against landing safety, and considering the invaluable protection offered by natural formations. the real work, the patient, meticulous preparation for human life, can begin. It's an undertaking of unprecedented scale and complexity, a symphony of engineering and autonomy playing out across millions of miles. The stark reality is that not everything colonists could possibly need would fit in one single spaceship to Mars. Imagine trying to pack an entire self-sustaining city, complete with all its infrastructure, machinery, and provisions, into a handful of vehicles. It's simply not feasible. Therefore, a series of several Forerunner missions will have to take place acting as quiet robotic pioneers. These missions wouldn't carry humans. Instead, they would transport the heavy machinery, the raw materials, and the autonomous robots necessary to begin laying the foundations autonomously for what the colonists will need. Think of them as advanced construction crews arriving long before the main party, silently and efficiently preparing the groundwork. These robots would be tasked with the initial arduous work excavating, building, setting up basic infrastructure, and ensuring the site is as ready as possible for human arrival. This pre-positioning of resources and autonomous construction minimizes the immediate burden on the first human crews, allowing them to focus on vital tasks rather than basic survival. It's like sending a swarm of industrious worker bees to prepare the hive before the queen and her colony arrive, ensuring that the new home is largely built and provisioned, ready for occupancy. This multi-phase approach is crucial for minimizing risk and maximizing the chances of success for the first human settlers, transforming a desolate landscape into a nascent outpost of humanity. As we continue our quiet journey towards the Red Planet, let us now gently turn our attention to the meticulous art of crafting a home on this alien world. Once a suitable site has been painstakingly chosen, a quiet triumph of data analysis and careful consideration, the true alchemy of transformation begins. This isn't just about constructing buildings. It's about weaving a protective, life-sustaining bubble in an environment that is fundamentally hostile to human life. And because no single spacecraft, no matter how vast, could carry all the intricate components of a functioning human habitat, the initial phases of this construction will be largely automated. A silent dance of intelligent machines preparing the stage for their human counterparts. Imagine a fleet of several Forerunner missions arriving long before the first human footsteps can ever disturb the Martian dust. These aren't manned vessels. They are cargo ships carrying the indispensable heavy machinery, the raw materials, and perhaps most importantly, legions of autonomous robots. These robots are the silent, tireless builders, the advance guard of humanity. They are tasked with the initial arduous work excavating vast quantities of Martian soil, preparing flat foundations, and meticulously setting up the basic infrastructure that will eventually support a human colony. This pre-positioning of resources and autonomous construction is crucial, a masterstroke of planning designed to minimize the immediate burden on the first human crews. It allows those brave pioneers to focus on vital high-level tasks upon arrival, rather than the backbreaking labor of basic survival and construction. Think of it as sending a swarm of incredibly industrious worker bees to prepare the hive long before the queen and her colony arrive, ensuring that the new home is largely built and provisioned, ready for immediate occupancy. This multi-phase automated approach is paramount for minimizing risk, maximizing efficiency, and ultimately boosting the chances of long-term success for the initial human settlers, transforming a desolate landscape into a nascent outpost of humanity. With the automated groundwork underway, the question turns to the very design of these future homes. How will they look? How will they function? This isn't merely an architectural challenge, it's a profound exercise in biomimicry and extreme engineering, where every design choice is a matter of life and death. To find the most ingenious solutions for long-lasting habitats, various organizations and visionaries have sponsored architectural competitions. These aren't just for show. They are serious endeavors to solicit the brightest minds from around the globe, encouraging them to push the boundaries of conventional design. While there is no single model that is said to be definitive, yet no one perfect blueprint that has emerged triumphant. The competitions have yielded a wide and inspiring variety of proposals, each more imaginative than the last. Some proposals speak of creating habitats using the very Martian ice translucent domes, perhaps allowing in diffused light while offering a degree of radiation protection. Imagine living within walls that shimmer with captured light, feeling both enclosed and connected to the stark beauty outside. Other ideas are more organic, drawing inspiration from the intricate growth patterns of fungi, envisioning structures that might grow or expand in modular self-assembling ways. This bio-inspired approach seeks to mimic nature's efficiency and adaptability, creating resilient and sustainable living spaces. Each proposal, no matter how fantastical it might seem, is meticulously thought out, balancing structural integrity, radiation, shielding thermal control, and the psychological well-being of future inhabitants. These design challenges are an exquisite blend of art and science, a testament to humanity's boundless creativity when faced with extraordinary constraints. The search for the ultimate Martian home is a continuous dialogue between the practical and the poetic, ensuring that our future dwellings are not just functional, but also inspire awe and comfort in equal measure. However, among this vibrant tapestry of architectural dreams, a clear front-runner concept has emerged, one that leverages the most abundant resource readily available on Mars, its soil. The majority of the suggestions utilize the regolith found all over the surface of Mars to build habitats. Regolith, the loose, unconsolidated dust and rocky material that covers the Martian landscape, might seem like an unlikely building material. Yet its very ubiquity makes it invaluable. The proposed method is to construct these habitats using 3D printing techniques through autonomous robots. Imagine a giant, silent 3D printer patiently extruding layers of Martian soil, slowly building up walls and roofs. Unfortunately, robots specifically designed and tested for this exact kind of extraterrestrial autonomous construction don't exist yet in their fully capable form. We have rovers, yes, and robotic arms, but the sophisticated, large-scale autonomous construction bots needed for this vision are still in the realm of advanced development. So these specialized machines have to be developed and rigorously tested before this idea even becomes a tangible possibility. But the basic concept is elegantly simple in its ambition. It requires excavating material from the surface, the ubiquitous regolith, which would then be processed and mixed with a critical ingredient, water ice. This mixture would transform the dusty regolith into something similar to concrete, a sturdy moldable material that can then be efficiently used for construction. The structure is then 3D printed layer by layer by these autonomous robots, meticulously following pre-programmed designs, gradually erecting the protective shell of the habitat. It's a vision of silent, diligent automation, a robot-driven ballet of creation under the alien sun, building the very first brick-and-mortar homes in humanity's new frontier. This technique, using local materials and advanced robotics, is seen as the most resource-efficient and sustainable path to establishing permanent structures on Mars, transforming the very ground beneath our feet into the walls that will protect our future. The vision of these 3D printing robots working tirelessly on the Martian surface brings us to a crucial realization. Robotic assistance and artificial intelligence will be invaluable in preparing the habitat for the colonists' arrival. This isn't just a matter of convenience, it's a fundamental necessity. Once humans arrive, they will be confined to their bulky pressurized suits, especially when undertaking any activities outside the safety of the habitat. Performing complex, intricate, or physically demanding tasks while encased in these suits would be an impossible burden. Imagine trying to wield heavy tools, connect delicate wiring, or engage in hard and prolonged manual labor while struggling against the stiffness and limited dexterity of a spacesuit. It would be akin to performing surgery with oven mitts or building a house while wearing diving gear. Therefore, the autonomous robots guided by advanced artificial intelligence will undertake the bulk of the initial strenuous work. They will be the tireless hands and eyes that can manipulate materials with precision, operate heavy machinery, and meticulously assemble complex components without the limitations imposed by human physiology or the need for life support. Their resilience to radiation and extreme temperatures and their ability to work continuously without rest make them the ideal workforce for the challenging Martian environment. They will lay the pipes, connect the power conduits, install the heavy equipment, and perform the initial calibration of life support systems. When the human colonists finally arrive, their primary focus can shift from basic construction to fine-tuning the systems activating the internal environments and conducting the scientific research that only humans can truly undertake. This collaborative symphony between human intellect and robotic precision is the key to unlocking the true potential of Martian colonization, allowing humanity to build not just structures, but a sustainable future in an utterly alien world. The robots are not just tools. They are essential partners in this grand, unprecedented endeavor, paving the way for human flourishing far from home. Once the primary structure of the habitat, meticulously 3D printed layer by layer from Martian regolith, is complete, a crucial final phase of protection begins. This structure, initially a robust shell, needs an additional layer of defense to truly make it a safe haven. It must be able to support the weight of additional regolith, the very soil from which it was constructed, piled on top of it. This isn't an aesthetic choice. It's a vital engineering requirement driven by the fundamental difference between Earth and Mars. On Earth, our vibrant, dynamic planet possesses a powerful magnetic field and invisible shield generated by its molten iron core, which gracefully deflects the vast majority of harmful cosmic radiation and solar particles, protecting all life on the surface. Mars tragically lost its global magnetic field billions of years ago. As a result, radiation is a big problem on the surface too, a constant, silent menace from the sun and deep space bathing the planet in dangerous energetic particles. Therefore, in the final phase of many of these habitat proposals, the solution is elegantly simple in its brute force. They recommend covering the habitat with more regolith, simply by shoveling it on top. This creates a thick protective blanket of Martian soil over the entire structure. Imagine a small hill or a gentle mound under which the pressurized human habitat quietly hums. This is because the more material there is between the sun and the colonists, the better they will be protected from its harsh, life-threatening radiation. The regolith acts as an effective physical barrier, absorbing and scattering the high-energy particles before they can penetrate the living spaces. It's a testament to the ingenuity of using what's available. The very ground beneath their feet becomes the ultimate shield. This protective layering is not merely a design feature. It is a fundamental aspect of survival on Mars, a quiet, continuous battle against the invisible currents of the cosmos. The layers of dust and rock become their most reliable guardians, allowing human life to flourish in a place where nature itself offers little inherent protection. With the habitats meticulously prepared, insulated, and shielded, the quiet hum of anticipation would begin to build. The groundwork laid the foundations, set the protective layers complete. Finally, the signal would be given, and the colonists can begin to arrive. This moment, the first human feet touching down near their future home, would be a crescendo of years, perhaps decades of preparation and dreaming. But their arrival isn't the end of the work. It's merely the beginning of the next equally demanding phase. Even with the tireless help of the autonomous robots who have so diligently toiled, the human colonists still have an immense amount to do before their new home is truly habitable. They would immediately need to connect up power from the primary energy sources, whether solar arrays or nuclear reactors, ensuring a steady flow of electricity to all systems. Then comes the complex task of setting up equipment within the habitats, installing scientific instruments, calibrating life support systems, arranging living quarters, and preparing the internal environment for long-term human occupancy. It's a colossal undertaking, a meticulous dance of engineering and logistics designed to generally get the site up and running. While this intricate process is going on, the colonists would most likely have to reside in temporary habitats. This could be their own spacecraft that brought them to Mars, serving as a rudimentary yet familiar shelter. Alternatively, they might utilize inflatable habitats, which are relatively lightweight to transport and can be quickly deployed to provide immediate shelter and a pressurized environment. In any case, these temporary dwellings would not be very spacious, offering only the absolute basics for survival. They would serve as a kind of cosmic camping trip, a temporary bivouac until the permanent structures are fully activated and ready to embrace their human occupants. It's a testament to the layered planning of Mars missions, acknowledging that even after arriving, comfort and full functionality are luxuries that must be earned through continued effort. The first moments on Mars are not of relaxation, but of urgent, purposeful activity, a race against the clock to transform raw construction into a living, breathing home, with the primary structures of humanity's Martian outpost meticulously 3D printed and carefully shielded against the harsh cosmic elements. And with the pioneering colonists having finally arrived, a profound transition begins. The temporary shelters, the cramped spacecraft, or the inflatable modules that served as their initial refuge will soon give way to more permanent abodes. The moment the permanent habitats are ready, a truly critical step must be taken. They will need to be pressurized. This isn't just about making them comfortable. It's about making them breathable, about creating a miniature bubble of Earth-like atmosphere in the midst of Mars's near vacuum. Imagine inflating a balloon within a larger desolate cavern, slowly filling it with the very essence of life, air. One ingenious method for creating this vital, breathable air on Mars involves a process called electrolysis. This is a remarkably elegant chemical separation, where water, that precious resource we've worked so hard to find and extract, is gently coaxed into revealing its constituent elements. By passing an electric current through water H2O, it cleanly splits into its fundamental components, hydrogen H2 and oxygen O2. The oxygen, of course, is the life-giving gas we breathe, essential for all biological processes. But electrolysis carries an added benefit. It also generates hydrogen. This hydrogen, far from being a waste product, can then be further refined into hydrazine as fuel. Hydrazine is a powerful propellant used in spacecraft thrusters and power systems, making this process a dual-purpose marvel, generating breathable air and simultaneously producing a vital energy source for return trips or further exploration. It's like a quiet, continuous factory humming within the habitat, tirelessly producing the very breath of life and the fuel for future adventures. Once this breathable environment, primarily composed of oxygen, mixed with a carefully calculated amount of nitrogen, which might need to be imported from Earth initially, or potentially extracted from trace amounts in the Martian atmosphere, though that's a much harder task, is generated, it needs to be efficiently sustained. This is where air recycling systems become indispensable. Fortunately, this isn't a new concept for humanity's ventures beyond Earth. This very technology is already being used by the International Space Station ISS, a testament to its proven reliability and effectiveness in closed-loop environments. Imagine the ISS, a tiny self-contained world orbiting Earth, where every breath taken by the astronauts is meticulously cleaned, filtered, and reoxygenated. Carbon dioxide is scrubbed out, moisture is condensed, and fresh oxygen is reintroduced, ensuring a continuous supply of clean, breathable air. This intricate network of pumps, filters, and chemical processes is the unsung hero of long-duration spaceflight, and its adaptation to Mars habitats will be critical. It's a quiet ballet of machines, ensuring that the air within the pressurized bubble remains fresh and invigorating, a constant reminder of our ability to recreate life's necessities, even in the most unforgiving of environments. Beyond the elegant simplicity of electrolysis, there's another innovative method to acquire oxygen, one that directly taps into Mars's most abundant atmospheric gas. While the Martian atmosphere is incredibly thin, it's overwhelmingly composed of carbon dioxide, CO2. About 95%. This seemingly hostile gas, toxic to humans in its raw form, holds the key to another potential source of breathable oxygen. This is precisely why the Perseverance rover also incorporates the MOXIE module, which stands for Mars Oxygen In Situ Resource Utilization Experiment. MOXIE isn't just a scientific instrument. It's an engineering marvel and experimental device designed to test the feasibility of converting Martian carbon dioxide into oxygen. It acts like a tiny tree, drawing in the alien air and exhaling breathable gas right there on the Martian surface. The MOXIE module works by using high temperatures to split carbon dioxide molecules, CO2, into oxygen O and carbon monoxide CO. The oxygen atoms then combine to form breathable O2. This experiment is a pivotal step in proving that future human missions could live off the land by generating their own oxygen, reducing the immense logistical burden of transporting all the oxygen from Earth. However, for both electrolysis and MOXIE, and indeed for most life-sustaining processes on Mars, a common thread emerges. Substantial energy production is needed. Splitting water, converting CO2, maintaining environmental controls, powering communications, growing food. All these vital functions demand a continuous, reliable, and significant source of power. It's like building a vibrant city only to realize that every single light bulb, every single appliance needs its own dedicated, robust power plant. The challenge then shifts from what we need to produce to how we produce the energy to make it all happen. One obvious and readily available source of energy familiar to us all on Earth is solar panels. They harness the abundant light from the sun, converting it into electrical power. A clean, quiet source of energy. However, on Mars, the efficiency of solar production is only about 40% of what you would get with the same solar panels on Earth. This significant drop is due to two primary reasons. Mars is further away from the sun, receiving less intense sunlight, and its atmosphere, though thin, can still scatter and absorb some of the incoming radiation. So while solar panels are a valuable component of a Martian energy strategy, they present inherent limitations. Moreover, solar power is helpful only half the time due to the day and night cycle on Mars, which is roughly equivalent to Earth's 24.6-hour day. During the long Martian night, solar panels produce no power, necessitating substantial battery storage or an alternative energy source. To complicate matters further, the Martian atmosphere, despite its thinness, is prone to powerful and pervasive weather events. Sandstorms sweep across the planet from time to time, ranging from localized dust devils to planet-encircling behemoths that can last for months. These dust storms are a notorious foe for solar-powered Martian missions. They can dramatically reduce the amount of sunlight reaching the panels, causing power levels to plummet, and the fine dust can accumulate on the panel surfaces, effectively choking off their ability to absorb light. We've seen this happen with past Martian missions, where once vigorous rovers and landers eventually fell silent, their solar panels buried or obscured by the relentless dust. So while solar power will undoubtedly play a role by itself, it isn't reliable enough for a colony that requires continuous uninterrupted power for life support and critical operations. It's like relying solely on a small, unpredictable stream for all your water needs. It simply won't sustain a thriving community. Given the inherent limitations and vulnerabilities of solar power on Mars, another crucial option for ensuring a stable and continuous energy source comes into focus: the development and deployment of a not yet invented cold nuclear reactor. While nuclear fission reactors are a proven technology on Earth, and compact versions have powered spacecraft for decades, like radioisotope thermoelectric generators, a truly robust, relatively small and cold fission reactor, capable of powering an entire colony for years, perhaps even decades, represents a significant engineering challenge. The term cold here refers to its ability to operate at relatively lower temperatures while still generating substantial power. making it safer and easier to manage in an extreme environment. The immense advantage of a nuclear reactor is its ability to guarantee a more stable energy source, providing continuous power regardless of the Martian day-night cycle or the fury of a planet-wide dust storm. It's like having a miniature artificial sun humming quietly beneath the habitat, providing a constant, unwavering flow of energy immune to the vagaries of Martian weather or orbital mechanics. Obviously, the most pragmatic and best solution incorporates a hybrid of both energy production methods, solar panels, to capture the free energy of sunlight when available, and a nuclear reactor to provide the essential baseline power and resilience. This dual approach offers redundancy and optimizes resource utilization. Solar panels can contribute significantly during the Martian day, reducing the burden on the nuclear reactor and allowing it to operate more efficiently, perhaps even storing excess power. The nuclear reactor, in turn, provides uninterrupted power during the night, during dust storms, and for critical life support systems that cannot tolerate any downtime. This hybrid system would be further augmented with reliable batteries to store power generated during peak production times. These batteries would act as buffers, providing instant power in the event of temporary outages, unexpected surges in demand, or emergencies. It's a multi-layered approach to energy security, a robust shield against the unpredictable nature of an alien world. The goal is to create an energy grid that is not just sufficient, but resilient, ensuring that the lights never go out, the air always flows, and the life support systems never falter, allowing the Martian settlers to thrive, not just survive. Beyond the fundamental needs of air and energy, the settlers would also need to meticulously consider the imperative to produce and purify water for consumption and other purposes. Water, as we've already established, is the very essence of life, a precious commodity on any world. Ideally, the Martian colony will be able to generate and provide 5 liters per settler per day for all their needs: drinking, cooking, hygiene, and eventually agriculture. This might sound like a challenging target, but it is entirely achievable because, thankfully, we know where to find water already on Mars in the form of water ice. Whether it's the vast gleaming expanses at the poles, the perennial icy lake within Korolev crater, or the hidden veins of permafrost beneath the surface, Mars holds significant reservoirs of frozen water. This readily available source significantly simplifies the initial stages of water procurement, transforming a potential crisis into a manageable engineering task. However, simply finding water ice is only the first step. The second equally critical step is to ensure that this water is continuously available and purified to human standards. This is where the concept of water recycling systems becomes paramount. Additionally, the colonies should meticulously incorporate such systems to minimize water waste to an absolute minimum. This is not just a good environmental practice, it's a non-negotiable requirement for survival in a closed-loop, resource-constrained environment. Every drop of water from laundry rinse to human waste must be treated as a precious resource to be meticulously recovered and purified. Once again, humanity doesn't have to invent this technology from scratch. It's already used effectively on the International Space Station ISS. The ISS, a floating laboratory of human ingenuity, demonstrates a remarkable capacity for water recovery, reclaiming nearly all the water used by its crew through sophisticated filtration and distillation processes. It's a testament to the fact that even in the most extreme environments, we can close the loop on essential resources, turning waste into life-sustaining bounty. The process of producing potable water from Martian ice is remarkably elegant in its simplicity, mirroring some of the most basic principles of Earth-based purification. Firstly, the production of water is as simple as extracting the ice from its Martian source, whether from the surface or subsurface. This might involve robotic excavation or even specialized melting probes. Once collected, this raw ice needs to be converted into its liquid form, so it's then cooked in an oven until it evaporates effectively, turning the solid ice into a gas steam, a process of sublimation and vaporization. This heating also serves to kill off any potential microbial contaminants. The resulting steam is then carefully condensed into liquid water, much like dew forming on a cold surface or rain condensing from clouds. Finally, this condensed water, though largely pure, undergoes a rigorous process of filtering again, using ceramic and carbon filters. These filters remove any lingering particulate matter, dissolved impurities, or organic compounds, ensuring the water is perfectly safe and palatable for human consumption. With these simple yet effective steps combined, extraction, heating, condensation, and multi-stage filtration, we have all the fundamental ingredients necessary to create a habitat suitable for life, an enclosed, protected environment with a steady, reliable production of breathable oxygen and clean, drinkable water. It's a closed-loop symphony of technology and resource management, transforming a desolate alien world into a burgeoning cradle for human civilization, ensuring that every breath and every sip is a testament to ingenuity and survival. With the fundamental life support systems humming quietly within their shielded abodes, the steady production of oxygen, the meticulous recycling of water, the Martian colonists would have secured the most basic necessities for survival. The pressurized environment, a fragile bubble of Earth-like conditions, now offers a safe space to breathe and drink. From this secure base, their gaze would naturally turn to the next great challenge, a primal human need that dates back to our earliest ancestors, the ability to grow plants for consumption. This isn't just about sustenance. It's about psychological well-being, about bringing a touch of green vibrancy to the desolate red landscape, a reminder of the verdant world they left behind. However, this endeavor of Martian agriculture comes with a significant and immediate obstacle to overcome. Although there is soil in the form of regolith found abundantly all over Mars, it is not immediately suitable for growing food. Think of it not as fertile earth soil, rich with organic matter and microbial life, but as finely ground rock, a dusty alien powder. The primary issue is that this regolith contains perchlorates, naturally occurring salts, that while not immediately lethal in small doses, are toxic for human consumption in large quantities. They can interfere with thyroid function and have other detrimental health effects. So simply sowing seeds into the Martian ground is not an option. A crucial preparation step is required. The regolith first has to be washed out with water, a painstaking process of rinsing away these harmful compounds, effectively leaching them out of the soil. This requires a significant amount of the colony's precious water, underscoring the interconnectedness of all Martian resource management. It's a delicate balance: use water to purify the soil, then use the purified soil to grow food, which in turn helps recycle some water. Once cleansed of its toxic substances, the regolith, now a blank canvas, still lacks the life-giving properties of earth soil. It needs to be treated and enriched. Specifically, the regolith needs to be treated with fertilizers, providing the essential nutrients that plants require for growth: nitrogen, phosphorus, potassium, and trace elements. These fertilizers might initially be brought from Earth or more sustainably generated within the colony itself through the processing of organic waste, a closed-loop system we'll touch on later. But even after this chemical enrichment, the soil is still primarily mineral. It lacks the airy, water-retentive texture that plants thrive in. Therefore, the treated soil must be mixed with organic matter so that it has the ideal texture for seeds to sprout, for roots to spread, and for water to be retained. This organic matter could come from various sources within the colony: human waste, processed into compost, leftover plant material, or even simple biomass grown specifically for this purpose. It's about transforming a sterile mineral dust into a living, breathing substrate, recreating a tiny piece of Earth's fertility on a foreign world. Despite these significant challenges, the prospect of growing food on Mars is not merely a theoretical exercise. Optimistically, a study already shows that it should be possible to grow plants on Mars and the Moon. This research, conducted in controlled environments, simulating extraterrestrial soils, provides compelling evidence that with proper treatment and nutrient augmentation, Martian regolith can support plant life. Imagine the quiet joy of the first green shoots emerging from the red dust, a vibrant symbol of resilience and hope. However, while the possibility of growing plants directly in treated regolith offers one pathway to self-sufficiency, there is another fascinating and highly efficient option that has gained significant traction for enclosed resource-limited environments: aquaponics. Aquaponics offers an elegant symbiotic solution to both food and protein production within a closed Martian ecosystem. It's a brilliant fusion of aquaculture, raising aquatic animals like fish, and hydroponics, growing plants in water without soil, creating a single harmonious and highly efficient system. In this environment, there is a fish pond, a contained aquatic habitat for fish. These fish play a crucial silent role in the system. They are responsible for delivering nitrates to the water with their feces. Fish waste, rich in ammonia, is naturally converted by beneficial bacteria into nitrites, and then nitrates, which are essential nutrients for plant growth. This nutrient-rich water is then pumped from the fish pond to the plant beds, where the plant roots absorb the nitrates, effectively cleaning the water for the fish before it cycles back to the pond. It's a beautiful self-sustaining loop, where fish waste becomes plant food and plants purify the fish's water, a perfect dance of give and take. For such closed systems, a particular type of fish has proven to be remarkably robust and widely used: tilapia. These versatile fish are often chosen for aquaponics systems because they feed on almost anything, from algae to plant scraps, making them incredibly efficient converters of organic matter. They also survive well in murky water and can tolerate a wide range of water conditions, a significant advantage in a pioneering Martian colony where perfect environmental control might be challenging. Moreover, and crucially for the colonists' diet, they are also edible. Tilapia could therefore become an important source of protein for the colonists, providing essential nutrients that might otherwise be difficult to acquire or transport from Earth. Imagine a quiet pond humming with life within the Martian habitat, a continuous source of fresh protein complementing the vegetables grown in the aquaponics beds. It's a truly ingenious way to maximize resource utilization and create a diverse, sustainable food source in an isolated environment, transforming a scientific concept into a vibrant, living ecosystem. Expanding on the principle of extreme resourcefulness, the idea of a fully self-sufficient Martian colony necessitates closing every loop, recycling every possible material. This includes what might seem at first glance like the least appealing resource: human feces and other organic waste. In these meticulously designed colonies, where every single resource will have to be reused and repurposed, human waste is not seen as simply refuse, but as a valuable input. It could also be used as fertilizer for the plants, just like in the aquaponics system. Through careful processing, perhaps composting, anaerobic digestion, or other bioremediation techniques, the organic matter in human waste can be broken down into nutrient-rich compounds, which can then be safely and effectively reintroduced into the agricultural systems. This might sound unappetizing, but it's a testament to the practicalities of survival in a truly closed environment. Every discarded piece of organic material, from leftover food scraps to human waste, becomes a building block for future sustenance. So just like with the energy production, where a hybrid approach was deemed wisest, perhaps it would be most prudent to use both systems for food production on Mars: aquaponics and regolith-based farming. The aquaponics system provides a reliable, high-yield source of fresh protein and vegetables, benefiting from the efficient nutrient cycling and water purification. It's a highly controlled, productive indoor farm. Simultaneously, regolith-based farming, using the treated and enriched Martian soil, could be developed perhaps for certain root vegetables or crops that thrive in a solid medium, or to provide a backup. This hybrid approach offers redundancy and resilience, diversifying the food sources and hedging against potential failures in one system. It also allows for the efficient utilization of all available organic waste, ensuring that nothing is truly wasted in the colony's precious ecosystem. In any case, whether through aquaponics or regolith farming, these farms will consume a lot of energy in the form of light. Plants, regardless of their growth medium, require specific wavelengths and intensities of light for photosynthesis, their vital process of converting light energy into chemical energy. This means large arrays of LED lights, carefully calibrated for optimal plant growth, humming within the habitat, drawing a significant portion of the colony's generated power. This energy demand adds another layer of complexity to the overall power budget. Furthermore, these sophisticated agricultural systems would need daily maintenance by the colonists. This isn't a passive system. It requires vigilant monitoring of water quality, nutrient levels, plant health, and fish well-being. It involves tasks like planning harvesting, pruning, feeding the fish, and troubleshooting any issues that arise. It's a constant hands-on commitment, an integral part of their daily routine, transforming them not just into astronauts, but into farmers of a new world. With all these intricate systems meticulously in place, a protected habitat, a closed-loop air supply, purified water, and efficient food production, the colony would in theory achieve a remarkable level of self-sufficiency. It would become a tiny independent island of humanity afloat in the vast Martian Ocean, largely independent of constant resupply from Earth. This self-reliance is the ultimate goal, the very definition of a sustainable off-world settlement. However, it is crucial to temper this vision of triumphant self-sufficiency with a dose of stark reality. It would not be an easy life. Far from the romanticized images of grand adventures, daily existence in a Martian colony would present an array of profound psychological and physical demands. Imagine a life confined to a small space, perhaps a series of interconnected modules with no immediate escape to the vast outdoors that defines human experience on Earth. The psychological impact of such confinement, week after week, month after month, would be immense. You would be stuck with the same people, your fellow colonists, a small, carefully selected group, with limited opportunity for new social interaction. This constant proximity without the natural ebb and flow of a larger society can breed tension, monotony, and a profound sense of claustrophobia, not just physically, but socially. The dietary experience, while designed for sustenance, would likely be restrictive, with colonists often eating the same things, primarily the outputs of their closed-loop agricultural systems. The vibrant culinary diversity of Earth would be a distant memory, replaced by the efficient, but perhaps monotonous fare of Martian-grown produce and tilapia. Beyond the confines and diet, the daily routine would be characterized by constant tasks and stress. Every system, every process would require vigilant monitoring and maintenance. A minor equipment failure could quickly escalate into a life-threatening emergency. The thin Martian atmosphere, the pervasive radiation, the very hostile nature of the outside world would be a constant, silent pressure. This relentless demand, this unwavering need for precision and vigilance, would make the psychological demands very taxing. It's a life of high stakes, where complacency could mean disaster, and where the weight of responsibility for the entire colony would rest heavily on every individual's shoulders. This constant pressure, coupled with the isolation, would test the very limits of human resilience, making mental fortitude as crucial as any technical skill. As we continue our quiet contemplation of life on Mars, having delicately woven the threads of sustenance and shelter, we must now turn our gaze inward towards the most intricate and perhaps most vulnerable aspect of a human colony, the human mind itself. For even with air to breathe, water to drink, and food to eat, the very essence of Martian existence would present a profound test of psychological resilience. This isn't just a scientific or engineering challenge, it's a deeply human one, probing the limits of our adaptability and mental fortitude. Consider for a moment that even on Earth, our vast, diverse, and interconnected planet, we have some very remote and lonely places where people live. Think of the dedicated scientists in Antarctica, dwelling for months in isolated research stations surrounded by endless ice and stark beauty with only a handful of colleagues for company. Or imagine the disciplined submarine crews living for weeks or months, submerged beneath the ocean's surface in a tightly confined metal tube, far from sunlight and fresh air, their world limited to the faces of their shipmates and the hum of machinery. These groups, remarkable for their endurance, undergo regular psychological checks to protect their mental health, a critical component of their mission protocols. Support systems are in place acknowledging the immense stress of their unique environments. And critically, even in these extreme situations, the people there always know that they can always be sent back home. There is an escape valve, a return ticket, a tangible connection to the familiar world that provides a profound sense of security, a lifeline in times of despair. But for colonists on Mars, this crucial safety net would be conspicuously absent. They are in a profound and unprecedented way trapped. There's no immediate turning back, no quick flight home if the psychological pressures become too great, if homesickness gnaws too deeply, or if interpersonal conflicts become unbearable. The sheer distance, the immense time and resources required for a return journey would make it an almost insurmountable barrier, if ever even an option. This stark reality, the knowledge that they are literally millions of miles from the nearest familiar comfort with no easy egress, would create a unique and relentless psychological burden. It's like sailing to a distant, uncharted island, burning your boats upon arrival, and knowing that your only path forward is to build a new life irrevocably cut off from your past. Therefore, only individuals with a truly strong mental fortitude could persevere in such an environment. They would need not only resilience, but an almost monastic ability to cope with monotony, isolation, and constant interpersonal proximity, developing coping mechanisms that stretch beyond conventional understanding. The Martian frontier demands not just physical pioneers, but psychological titans. Beyond the invisible pressures on the mind, the very physical environment of Mars presents another more tangible set of challenges, particularly related to its diminished gravitational pull. Mars has approximately 1/3 of Earth's gravity. While this might sound liberating, like a permanent sense of lightness, it carries profound and largely unexplored implications for the human body over extended periods. We've had a glimpse into these challenges through experiments conducted in microgravity, such as the famous zero-gravity experiment with the Kelly twins on the International Space Station ISS. Astronaut Scott Kelly spent nearly a year in orbit, while his identical twin brother Mark remained on Earth, providing a unique comparative study. The results brought up several serious health issues associated with prolonged exposure to microgravity, which would likely be exacerbated or at least manifested differently in Mars's low-gravity environment. These health issues are concerning and wide-ranging. They include a significant loss of muscle and bone mass, as the body no longer needs to exert itself against Earth's constant gravitational pull, leading to a rapid weakening of the musculoskeletal system. Imagine your bones becoming brittle and your muscles atrophying, making even simple tasks difficult. Astronauts also experience vision problems, often due to shifts in fluid distribution in the head, causing pressure on the optic nerve. There's a poor fluid distribution throughout the body, with fluids tending to pool in the upper body and head, leading to puffy faces and thin legs, and potentially impacting cardiovascular health. A loss of balance sense is also common, as the inner ear, accustomed to Earth's gravity, struggles to reorient itself in a different or absent gravitational field. Furthermore, there have been observations of spine misalignment, as the discs between vertebrae expand in the absence of compression, leading to back pain and potential nerve issues. Crucially, prolonged spaceflight can also lead to cardiovascular problems, as the heart, no longer needing to work as hard against gravity to pump blood, becomes less efficient. Finally, A weaker immune system is another significant concern, making astronauts more susceptible to illness and infection at a time when medical resources are extremely limited. While we don't know exactly how the human body will cope in a low-gravity environment for extended periods, Mars's one-third gravity is different from the near-zero gravity of the ISS. It is highly probable that settlers on Mars may struggle with some of these issues too. The difference in gravity might change the rate or severity of these problems, but the underlying physiological challenges remain. The body is finely tuned to Earth's gravity, and any deviation, whether extreme microgravity or reduced gravity, prompts a complex set of physiological adaptations that are often detrimental in the long run. To counteract these inherent risks, to wage a constant battle against the body's tendency to decondition in low gravity, the settlers will have to undertake a significant amount of exercise. This isn't just about staying fit. It's a critical medical countermeasure demanding hours of dedicated physical activity each day to maintain muscle and bone density and to keep the cardiovascular system robust. This necessary exercise regimen further lengthens their working hours, adding another layer of demand to an already incredibly busy and stressful schedule. It's a relentless commitment to their physical well-being, a daily ritual to defy the subtle but pervasive forces of an alien world, slowly reshaping their very beings. The sheer magnitude of these biological and psychological challenges has driven scientists and mission planners to consider increasingly radical solutions, pushing the boundaries of what it means to be human. NASA, in its far-sighted projections for long-duration missions, has even gone as far as to seriously contemplate genetic modifications for the astronauts who embark on these protracted stays beyond Earth. This isn't science fiction anymore. It's a tangible, albeit highly controversial area of research. The idea is to genetically enhance astronauts to combat the inherent dangers of radiation exposure and the debilitating effects of microgravity, among other threats. Imagine modifying genes to make cells more resistant to radiation damage or to stimulate bone and muscle growth, even in reduced gravity. This could involve techniques such as gene editing, like CRISPR, to alter specific sequences of DNA, or gene therapy to introduce beneficial genes. From a purely technological standpoint, some aspects of this could even be plausible with current technology or with advancements anticipated in the near future. We are already developing gene therapies for various medical conditions on Earth. However, this profound intersection of biology ethics and space exploration immediately raises a lot of controversy on the moral limits of such manipulation. Where do we draw the line? Is it ethical to alter the very blueprint of human life for the sake of space exploration? What are the long-term unforeseen consequences of such modifications, not just for the individual, but for the human gene pool? Who decides what constitutes a beneficial modification? These are not easy questions, and they ignite passionate debates touching upon our deepest values and our understanding of human nature. The ethical landscape of genetic modification for space travel is as vast and uncharted as space itself, a silent philosophical challenge accompanying the scientific quest. Still, even with all these daunting considerations, the psychological isolation, the physical toll of low gravity, and the complex ethical questions surrounding radical solutions, there remains an undeniable, almost magnetic allure to the Martian dream. There is certainly no shortage of volunteers wanting to go. In fact, every time there's been an opportunity, whether it's a call for astronaut applications for government programs or a private initiative seeking participants for a simulated mission or even a one-way trip, agencies and companies have received a barrage of applications from hopeful candidates. These individuals come from all walks of life, united by a common thread, an insatiable curiosity, an unyielding, adventurous spirit, and a profound desire to be part of something truly monumental, something that transcends the ordinary boundaries of human experience. This unwavering enthusiasm speaks volumes about the human spirit. It tells us that, despite the immense risks and the profound sacrifices required, the call of the unknown, the promise of a new frontier, remains an incredibly powerful motivator. It suggests that deep within us lies an innate drive to explore, to expand, and to leave our mark on the cosmos. These aspiring colonists are not merely seeking escape, they are seeking purpose, meaning, and the chance to contribute to a legacy that will span generations. They are the torchbearers of humanity's pioneering spirit, willing to brave unimaginable dangers for the sake of a greater dream. Their willingness to venture forth even into such a challenging environment is a testament to the enduring power of human aspiration and the quiet, persistent pull of that distant red planet. Ultimately, the grand vision of establishing these colonies on Mars will depend on how technology evolves here on Earth. Our capabilities in robotics, in artificial intelligence, in closed-loop life support systems, in advanced materials, in energy generation, and even in biotechnology. All these interconnected fields are the silent drivers of our Martian destiny. While at the moment it seems that we already have a lot of what is necessary to create basic bases outside of Earth, we don't yet possess all of what is truly needed for sustainable, thriving settlements. There are still significant gaps, critical technologies that need to be refined, miniaturized, made more robust, and more energy efficient. It's a continuous race against the clock, a relentless pursuit of innovation, driven by the distant promise of a Martian future. Perhaps with continued dedication, with breakthroughs we can barely imagine today, within our lifetime, there really will be colonies on Mars. Imagine gazing up at the night sky, pointing out that tiny red speck, and knowing that somewhere on its surface, humans are breathing, living, and building a new civilization. It's a thought that fills the heart with quiet wonder and boundless hope, a testament to the enduring power of the human dream. Well, that's all we have time for today. Curious minds and sleepy thinkers, I hope you've enjoyed drifting through this exploration of the colonization of Mars, allowing these grand ideas to gently settle in your mind. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics, where we can continue to explore the mysteries of the universe together, always at a pace gentle enough not to disturb your peaceful repose. But for now, I'm Alex McCone, and this has been Astrum. All the best, and see you next time, perhaps under a different sky, having gently explored the monumental challenges of reaching Mars and establishing the physical framework of a colony, the habitats, the air, the water, the food. We must now turn our quiet attention to the often unseen yet profoundly impactful burdens that would weigh upon the human spirit. For even with all the technological marvels in place, the daily existence in a Martian colony would be a unique and relentless test of psychological resilience, far removed from the romanticized visions of space exploration. This part of our journey delves into the quiet corners of the human mind, revealing the subtle yet powerful pressures of an utterly alien existence. Imagine a life confined to a small space, perhaps a series of interconnected modules, each designed for maximum efficiency but minimal sprawl. There would be no sprawling landscapes, no open skies to escape to, no vast horizons to stretch your gaze. The boundaries of your world would be the walls of your habitat, the sterile hum of the life support systems, and the limited vistas of the Martian surface, seen through thick, often dusty windows. This spatial limitation is not merely a physical constraint. It's a psychological one, fostering feelings of claustrophobia and a pervasive sense of monotony. The familiar rhythms of Earth, the subtle variations of daylight filtering through a window, the distinct scent of rain on soil, the feeling of wind on your skin, all these sensory anchors of our existence would be replaced by an artificially controlled environment, carefully maintained, but ultimately static. This constant unchanging backdrop can slowly, insidiously erode one's sense of vibrancy and spontaneity, turning days into a blurred succession of regulated tasks within a confined bubble. It's a profound shift from the boundless freedom of Earth to the meticulously managed existence of an extraterrestrial outpost, where every breath, every movement is carefully calibrated and contained. Adding to the quiet pressure of confinement is the unavoidable reality of being stuck with the same people. A Martian colony, at least initially, would be a small, tightly knit group. Your fellow colonists carefully selected for their skills and psychological stability. While these bonds would undoubtedly grow incredibly strong, forged in the crucible of shared purpose and immense challenge, the constant proximity, week after week, month after month, year after year, without the natural ebb and flow of a larger, more diverse society, can become a unique source of stress. Personal quirks, minor annoyances, and even simple habits that might go unnoticed in a bustling Earth environment would become magnified, amplified by the lack of personal space and the absence of fresh faces. It's like an extremely long road trip, but with no possibility of pulling over, no option to step outside and clear your head, and no new towns or landscapes to break the routine. The dynamics within the crew would be under constant scrutiny, requiring an extraordinary level of patience, communication, and mutual understanding. Every interaction, every conflict would carry a greater weight, as the social fabric of the entire colony depends on the harmony of its few members. The ability to manage interpersonal relationships, to offer grace and forbearance, becomes as crucial a survival skill as any technical expertise. The dietary experience, too, would contribute to this sense of confinement and monotony. While meticulously designed for nutritional sustenance, the food would likely be restrictive, with colonists often eating the same things. Primarily, the carefully cultivated outputs of their closed-loop agricultural systems. Imagine the absence of fresh, varied produce from Earth's sprawling farms, the rich culinary diversity of global cuisines, the joy of a spontaneous meal at a new restaurant. Instead, their diet would largely consist of Martian-grown vegetables, perhaps some fungi, and the protein from the aquaponics system, like tilapia. While perfectly nutritious, this lack of variety, the predictable repetition of flavors and textures, can lead to a quiet psychological burden, a subtle erosion of one of life's simple pleasures. It's a reminder of what has been left behind, a small sacrifice in the grand scheme of colonization, but one that can weigh heavily on the spirit over time, adding to the pervasive feeling of being confined, not just physically, but gastronomically. Beyond the physical and sensory confines, the daily routine would be characterized by constant tasks and stress. Life on Mars would be far from leisurely. Every system, every process, from air recycling to water purification, from plant cultivation to equipment maintenance, would require vigilant monitoring and meticulous attention. A minor equipment failure, a slight deviation in an atmospheric reading, a hint of trouble in the hydroponic system could quickly escalate into a life-threatening emergency. The thin Martian atmosphere, the pervasive radiation from outside, the sheer hostile nature of the external world would be a constant, silent pressure, an omnipresent threat looming just beyond the habitat walls. This relentless demand for precision, for vigilance, for problem-solving under pressure would make the psychological demands very taxing. There would be little room for complacency, little opportunity for true relaxation. It's a life of high stakes where every individual carries a piece of the collective responsibility for the colony's survival. This constant pressure, coupled with the profound isolation, would test the very limits of human resilience, making mental fortitude as crucial a survival skill as any technical expertise. The Martian frontier demands not just physical pioneers, but psychological titans capable of enduring the unyielding stress of a life where every moment is a quiet battle against the odds. To truly grasp the unique psychological burden of Martian life, it's helpful to consider parallel experiences on Earth, yet also acknowledge their critical differences. Even on our vast, diverse, and interconnected planet, we have places that push the boundaries of human endurance and isolation. Think of the dedicated scientists living and working in Antarctica, enduring months of extreme cold, perpetual daylight or darkness, and often complete isolation from the outside world. Their research stations are small, self-contained bubbles of human activity, surrounded by an endless expanse of ice. Or imagine the disciplined submarine crews living for weeks or even months, submerged beneath the ocean's surface in a tightly confined metal tube, far from sunlight, fresh air, and the rhythms of the terrestrial world. Their universe shrinks to the faces of their shipmates and the constant hum of machinery. These groups, remarkable for their tenacity and psychological strength, undergo regular psychological checks as a standard part of their mission protocols. Support systems are meticulously in place, acknowledging the immense stress of their unique, demanding environments. Debriefings, counseling, and recreational activities are all designed to mitigate the psychological toll. But here lies the profound existential difference that sets Martian colonists apart in these extreme earthbound situations. The people there always know that they can always be sent back home. There is an escape valve, a return ticket, a tangible connection to the familiar world that provides a profound sense of security, a lifeline in times of despair. A scientist in Antarctica knows that eventually a supply ship will arrive, or a plane will come to take them back to civilization. A submariner knows that their mission will end, and they will resurface to sunlight and the embrace of loved ones. This very knowledge, this invisible thread connecting them to home, provides a crucial psychological buffer, a deep well of resilience. For colonists on Mars, however, this crucial safety net would be conspicuously absent. They are in a profound and unprecedented way trapped. There's no immediate turning back, no quick flight home if the psychological pressures become too great, if homesickness gnaws too deeply, or if interpersonal conflicts become unbearable. The sheer distance, the immense time, months, perhaps years, and the astronomical resources required for a return journey would make it an almost insurmountable barrier, if ever even an option for individuals beyond their initial mission parameters. This stark reality, the knowledge that they are literally millions of miles from the nearest familiar comfort with no easy egress, no quick escape, would create a unique and relentless psychological burden. It's like sailing to a distant uncharted island and then, upon arrival, symbolically burning your boats, knowing that your only path forward is to build a new life irrevocably cut off from your past. Therefore, only individuals with a truly strong mental fortitude could persevere in such an environment. They would need an almost superhuman level of resilience, self-awareness, and adaptability. They would require not just the ability to cope with monotony and isolation, but an almost monastic capacity to manage constant interpersonal proximity, developing coping mechanisms that stretch beyond conventional understanding. Their internal landscapes would need to be as vast and resilient as the cosmos outside their habitat. The Martian frontier demands not just physical pioneers capable of operating complex machinery, but psychological titans who can navigate the intricate, often turbulent currents of the human mind under extreme duress. Their mental strength would be their most vital tool, their most robust shield against the invisible, pervasive pressures of an alien world. The sheer weight of this one-way journey, the implicit finality of their decision, would permeate every moment, shaping their perceptions, their interactions, and their very sense of self in a way few humans have ever experienced. Beyond the unseen pressures on the mind, the very physical environment of Mars presents another more tangible set of challenges, particularly related to its diminished gravitational pull. Mars has approximately 1/3 of Earth's gravity. While this might sound like a fascinating, even liberating experience, imagine feeling perpetually lighter, able to jump higher, lift heavier objects with ease. It carries profound and largely unexplored implications for the human body over extended periods. Our bodies, having evolved over billions of years under the constant embrace of Earth's gravity, are exquisitely tuned to its pull. Any significant deviation from this familiar force initiates a complex cascade of physiological adaptations, many of which are detrimental in the long run. We've already had a glimpse into these challenges through experiments conducted in microgravity environments, such as the famous zero-gravity experiment, with the Kelly twins on the International Space Station, ISS. Astronaut Scott Kelly spent nearly a year in orbit, experiencing the near weightlessness of space, while his identical twin brother Mark remained on Earth, providing a unique comparative study. The results of this pioneering research brought up several serious health issues associated with prolonged exposure to microgravity issues that would likely be exacerbated or at least manifested differently in Mars's 1/3 gravity environment. It's a sobering reminder that while space is vast and inviting, it is fundamentally an unnatural place for human physiology. These health issues are concerning and wide-ranging, painting a stark picture of the body's struggle to adapt. One of the most significant problems is a rapid and profound loss of muscle and bone mass. Without the constant load of Earth's gravity pushing down, the body perceives no need to maintain dense bone or powerful muscles. Bones can become brittle, increasing the risk of fractures, and muscles can atrophy, making even simple tasks difficult and contributing to overall weakness. Imagine returning to Earth after years on Mars, feeling like your own body is no longer entirely your own, weakened and frail. Astronauts also experience significant vision problems, often referred to as spaceflight-associated neuroocular syndrome, SAS, believed to be caused by shifts in fluid distribution in the head, causing increased intracranial pressure that can flatten the optic nerve and permanently alter eye shape. Furthermore, there's a poor fluid distribution throughout the body, with fluids tending to pool in the upper body and head, leading to puffy faces and thin, atrophied legs. This fluid shift can also impact cardiovascular health, as the heart, no longer needing to work as hard against gravity to pump blood upwards, becomes less efficient over time. Its muscles can weaken, and it may struggle to readapt upon return to a higher gravity environment. A loss of balance sense is also a common complaint, as the inner ear, a crucial organ for balance accustomed to Earth's strong gravitational cues, struggles to reorient itself in a different or absent gravitational field. This can lead to disorientation and difficulty with movement. Moreover, there have been observations of spine misalignment as the discs between vertebrae expand in the absence of compression, leading to chronic back pain and potential nerve issues. Finally, and crucially for survival in a hostile environment, prolonged spaceflight can also lead to a weaker immune system, making astronauts more susceptible to illness and infection. At a time when medical resources are extremely limited and evacuation impossible, each of these physiological changes represents a formidable challenge to long-term human health and well-being on Mars. While we don't know exactly how the human body will cope in a low-gravity environment for extended periods, Mars's 1/3 gravity is a unique intermediate point, different from both Earth's full gravity and the near-zero gravity of the ISS. It is highly probable that settlers on Mars may struggle with some of these issues too. The exact rate or severity of these problems might differ from what we see in microgravity, but the underlying physiological challenges remain. The body is finely tuned to Earth's gravity, and any deviation, whether extreme microgravity or reduced gravity, prompts a complex set of physiological adaptations that are often detrimental in the long run. It's a constant battle against the body's innate tendency to decondition in a less demanding gravitational field. To counteract these inherent risks, to wage a constant battle against the body's tendency to decondition in low gravity, the settlers will have to undertake a significant amount of exercise. This isn't just about staying fit or maintaining physical appearance. It's a critical medical countermeasure, a non-negotiable part of their daily routine. They will need to dedicate hours each day to rigorous physical activity, employing specialized equipment designed to simulate Earth's gravitational loads to maintain muscle and bone density, and to keep the cardiovascular system robust. This necessary, demanding exercise regimen further lengthens their working hours, adding another layer of demand to an already incredibly busy and stressful schedule. It's a relentless commitment to their physical well-being, a daily ritual to defy the subtle but pervasive forces of an alien world, slowly reshaping their very beings pushing them to their physical limits, even within their new home. The treadmill, the resistance, bans the quiet strain of muscles working against artificial loads. These will become as familiar a part of their Martian life as the red dust outside. As we continue our introspective journey, having touched upon the profound psychological and physiological strains of Martian life, we arrive at a frontier that challenges not only our engineering prowess, but also our deepest ethical considerations. The sheer magnitude of the biological and psychological hurdles facing long-duration space travel, particularly a mission to Mars, has compelled scientists and mission planners to consider increasingly radical solutions, pushing the very boundaries of what it means to be human. In this realm of audacious thought, NASA, in its far-sighted projections for long-duration missions, has even gone as far as to seriously contemplate genetic modifications for the astronauts who embark on these protracted stays beyond Earth. This isn't merely the stuff of science fiction anymore. It's a tangible, albeit highly controversial area of cutting-edge research. The underlying idea is elegantly simple in its ambition to genetically enhance astronauts to combat the inherent dangers of space, particularly the debilitating effects of radiation exposure and the profound physiological impact of microgravity, among other threats. Imagine for a moment a future where we could genetically engineer human cells to be inherently more resistant to radiation damage, making them less susceptible to cancer and other cellular malfunctions caused by cosmic rays. Or perhaps to stimulate bone and muscle growth even in reduced gravity environments, effectively hardwiring the body to resist the deconditioning that currently plagues astronauts. This could involve sophisticated techniques such as gene editing like CRISPR to precisely alter specific sequences of DNA within an astronaut's cells, or gene therapy, introducing beneficial genes that produce protective proteins or enhance cellular repair mechanisms. From a purely technological standpoint, some aspects of this audacious vision could even be plausible with current technology or with advancements anticipated in the very near future. The pace of genetic engineering and biotechnology on Earth is accelerating at an astonishing rate. We are already developing and implementing gene therapies for various medical conditions, from rare genetic disorders to certain cancers, demonstrating our growing ability to manipulate the human genome. The leap to applying these techniques for space adaptation, while immense, is no longer purely fantastical. However, this profound intersection of biology, ethics, and space exploration immediately raises a lot of controversy on the moral limits of such manipulation. This isn't just about treating a disease, it's about proactively altering the fundamental biological blueprint of a healthy human being for a specific purpose. Where do we draw the line? Is it ethical to fundamentally alter the very essence of human life for the sake of space exploration? No matter how noble the goal. What are the long-term unforeseen consequences of such modifications? Not just for the individual astronaut, but for the human gene pool for future generations, for our very definition of humanity. Who decides what constitutes a beneficial modification versus an unacceptable alteration? These are not easy questions, and they ignite passionate debates touching upon our deepest values, our understanding of human nature, and the very concept of natural evolution versus engineered adaptation. The ethical landscape of genetic modification for space travel is as vast and uncharted as space itself. A silent philosophical challenge accompanying the bold scientific quest, forcing us to ponder not just what we can do, but what we should do. Still, even with all these daunting considerations, the profound psychological isolation, the relentless physical toll of low gravity, the intricate engineering challenges, and the complex ethical questions surrounding radical biological solutions, there remains an undeniable, almost magnetic allure to the Martian dream. It speaks to a deeply ingrained part of the human spirit, the insatiable drive to explore, to expand, and to transcend boundaries. And remarkably, for all the inherent dangers and sacrifices, there is certainly no shortage of volunteers wanting to go to Mars, In fact, every time there's been an opportunity. Whether it's a formal call for astronaut applications, for government space agency programs like NASA or ESA, or a bold announcement from a private initiative seeking participants for a simulated mission, or even a theoretical one-way trip, the response has been overwhelming. Agencies and companies have consistently received a barrage of applications from hopeful candidates. These individuals come from all walks of life, from diverse professional backgrounds, and across various age groups united by a common thread: an unshakable curiosity, an unyielding adventurous spirit, and a profound desire to be part of something truly monumental. Something that transcends the ordinary boundaries of human experience. They are driven by a sense of purpose, a yearning for discovery, and perhaps a quiet conviction that humanity's future lies beyond Earth. This unwavering enthusiasm, this cascade of eager volunteers, speaks volumes about the enduring power of the human spirit. It tells us that despite the immense risks and the profound sacrifices required, the separation from loved ones, the unknown health consequences, the near irreversible nature of the journey, the call of the unknown, the promise of a new frontier, remains an incredibly powerful motivator. It suggests that deep within us lies an innate, almost primal drive to explore, to expand, and to leave our mark on the cosmos. These aspiring colonists are not merely seeking escape from terrestrial woes. They are seeking purpose, meaning, and the chance to contribute to a legacy that will span generations, perhaps even millennia. They are the torchbearers of humanity's pioneering spirit, willing to brave unimaginable dangers for the sake of a greater dream. Their willingness to venture forth even into such a challenging and unforgiving environment is a testament to the enduring power of human aspiration and the quiet, persistent pull of that distant red planet. It's a reminder that courage isn't just about facing visible dangers, but also about embracing the profound uncertainties that lie beyond the edge of the known. Ultimately, the grand vision of establishing these colonies on Mars will profoundly depend on how technology evolves here on Earth. Our journey to Mars is not just about building a single magnificent spacecraft. It's about fostering a continuous exponential growth in our technological capabilities across a vast array of interconnected fields. Think of it as a complex, multi-threaded tapestry being woven simultaneously, advancements in robotics to perform autonomous construction and maintenance, breakthroughs in artificial intelligence to guide these robots and manage complex life support systems, innovations in closed-loop life support systems to achieve unprecedented levels of self-sufficiency in air, water, and waste recycling, the development of lighter, stronger, and more radiation-resistant advanced materials for habitats in spacecraft, the creation of highly efficient and reliable energy generation systems that can operate independently of sunlight, perhaps small cold nuclear reactors, and, as we've just discussed, even radical advancements in biotechnology to enhance human resilience. All these interconnected fields are the silent drivers of our Martian destiny, each a vital thread in the grand design. While at the moment, it seems that we already have a significant portion of what is necessary to create basic bases outside of Earth, enough to launch missions, land rovers, and conduct short-duration human spaceflight. We don't yet possess all of what is truly needed for sustainable, thriving settlements. There are still significant gaps, critical technologies that need to be refined, miniaturized, made more robust, and more energy efficient. It's a continuous race against the clock, a relentless pursuit of innovation, driven by the distant promise of a Martian future. The journey from a rudimentary outpost to a self-sustaining colony is not just a few steps, but a series of monumental leaps, each requiring dedicated research, immense investment, and collaborative effort across nations and private entities. Perhaps with continued dedication, with the kind of breakthroughs we can barely imagine today within our lifetime, there really will be colonies on Mars. Imagine gazing up at the night sky, pointing out that tiny red speck, and knowing that somewhere on its surface, humans are breathing, living, working, and building a new civilization. It's a thought that fills the heart with quiet wonder and boundless hope, a testament to the enduring power of the human dream, the profound capacity of our species to adapt, to innovate, and to reach for new horizons. It implies a future where humanity's story is no longer confined to a single planet, but unfolds across the vast inviting canvas of the cosmos, making us true citizens of the solar system. This is the quiet, powerful promise that Mars holds a silent beacon of our expanding destiny, urging us ever onward. As we gently approach the close of our journey, having traversed the vast distances and intricate challenges of the Martian dream, we find ourselves reflecting on the very essence of humanity's drive to reach beyond Earth. This final chapter isn't just about the tangible technologies or the engineering feats. It's a quiet contemplation of the spirit that propels us, the enduring call of the unknown, and the profound questions of our destiny. Central to the realization of any Martian future is the boundless interest in human resource that fuels this colossal ambition. Despite the immense risks, the profound isolation, and the daunting physical and psychological tolls we've discussed, there remains an undeniable, almost magnetic allure to the Martian dream. It speaks to a deeply ingrained part of the human spirit, the insatiable drive to explore, to expand, and to transcend boundaries. And remarkably, for all the inherent dangers and sacrifices required, the separation from loved ones, the unknown health consequences of a new gravitational environment, the near irreversible nature of the journey, there is certainly no shortage of volunteers wanting to go to Mars. This is a powerful testament to the adventurous core of our species. In fact, every time there's been an opportunity, whether it's a formal call for astronaut applications for government space agency programs like NASA or the European Space Agency, or a bold announcement from a private initiative seeking participants for a simulated mission on Earth, or even a theoretical one-way trip, the response has been overwhelming. Agencies and companies have consistently received a barrage of applications from hopeful candidates. These individuals come from all walks of life, from diverse professional backgrounds: engineers, doctors, scientists, artists, and even those with no specific space-related training, all united by a common thread. They share an unshakable curiosity, an unyielding, adventurous spirit, and a profound desire to be part of something truly monumental, something that transcends the ordinary boundaries of human experience. They are not merely seeking escape from terrestrial woes. They are seeking purpose, meaning, and the chance to contribute to a legacy that will span generations, perhaps even millennia. They are the torchbearers of humanity's pioneering spirit, willing to brave unimaginable dangers for the sake of a greater dream, a vision of human presence on another world. Their willingness to venture forth even into such a challenging and unforgiving environment is a testament to the enduring power of human aspiration and the quiet, persistent pull of that distant red planet. It's a profound reminder that courage isn't just about facing visible dangers. It's also about embracing the deep uncertainties that lie beyond the edge of the known, driven by an inner fire that compels us to reach higher, further. This human capital, this wellspring of daring individuals, is perhaps the most critical resource of all, for without the human will, no technology, however advanced, can turn a dream into reality. Ultimately, the grand vision of establishing these colonies on Mars will profoundly depend on how technology evolves here on Earth. Our journey to Mars is not just about building a single magnificent spacecraft. It's about fostering a continuous exponential growth in our technological capabilities across a vast array of interconnected fields. Think of it as a complex, multi-threaded tapestry, being woven simultaneously, each strand representing a crucial area of innovation. Advancements in robotics, for instance, are essential for autonomous construction, resource extraction, and maintenance on Mars, minimizing the risk into human pioneers. Imagine fleets of silent, industrious machines preparing the ground-assembling structures and managing complex systems long before human boots touch the surface. Breakthroughs in artificial intelligence are equally vital, needed to guide these autonomous robots to manage intricate life support systems with predictive precision and to process vast amounts of data, acting as an omnipresent intelligent guardian for the colony. Innovations in closed-loop life support systems are paramount, pushing the boundaries of self-sufficiency in air, water, and waste recycling to unprecedented levels, ensuring every molecule is reused and repurposed. This means more efficient air scrubbers, advanced water purification, and bioregenerative systems that turn waste into valuable resources, creating a truly sustainable mini-biosphere. The development of lighter, stronger, and more radiation-resistant advanced materials is critical for both spacecraft and habitats, allowing us to build structures that are both resilient to the Martian environment and efficient to transport. This might involve new composites, ceramics, or even smart materials that can adapt to changing conditions. Furthermore, the creation of highly efficient and reliable energy generation systems that can operate independently of sunlight is crucial. This is where the development of small, cold nuclear reactors capable of providing continuous stable power regardless of dust storms or the Martian night becomes a game changer. And as we've just discussed, radical advancements in biotechnology are being explored to enhance human resilience, perhaps even to genetically adapt our bodies to better withstand the unique stresses of space and low gravity. All these interconnected fields are the silent drivers of our Martian destiny, each a vital thread in the grand design. They represent the tireless work in laboratories, the breakthroughs in universities, and the ingenuity in private companies, all converging towards a shared extraterrestrial future. The pace of innovation on Earth directly dictates the pace of our expansion into the cosmos, while at the moment it seems that we already have a significant portion of what is necessary to create basic bases outside of Earth, enough to launch missions, land sophisticated rovers, and conduct short-duration human spaceflight to the International Space Station. We don't yet possess all of what is truly needed for sustainable, thriving settlements. There are still significant gaps, critical technologies that need to be refined, miniaturized, made more robust, and made even more energy efficient. It's a continuous race against the clock, a relentless pursuit of innovation, driven by the distant promise of a Martian future. The journey from a rudimentary outpost, a mere scientific station, to a truly self-sustaining colony, a second home for humanity, is not just a few steps, but a series of monumental leaps. Each leap will require dedicated research, immense investment, unparalleled collaborative effort across nations and private entities, and perhaps a few more failures and lessons learned along the way. This phase of development is not just about building machines, but about perfecting the very art of extraterrestrial living, anticipating every need and engineering every solution with meticulous care. Perhaps, and this is the quiet hope that hums beneath all the scientific and engineering complexities, within our lifetime there really will be colonies on Mars. Imagine gazing up at the night sky, pointing out that tiny red speck, and knowing that somewhere on its surface, beneath a protective dome, or within a sheltered lava tube, humans are breathing, living, working, and building a new civilization. It's a thought that fills the heart with quiet wonder and boundless hope, a testament to the enduring power of the human dream, the profound capacity of our species to adapt, to innovate, and to reach for new horizons. It implies a future where humanity's story is no longer confined to a single planet, but unfolds across the vast inviting canvas of the cosmos, making us true citizens of the solar system. This isn't just about escape or survival. It's about expansion, about understanding, and about the intrinsic human desire to explore what lies beyond. It's about ensuring that the flickering candle of human consciousness, once confined to one fragile world, can ultimately ignite new flames across the galaxy. The red glow of Mars, once a symbol of war and mystery, is slowly transforming into a beacon of hope and a promise of a multi-planetary future for humankind. The children born in these Martian colonies, seeing Earth as a distant, beautiful blue star, will redefine what it means to be human, to be home. their very existence will be a living testament to the generations of dreamer scientists and adventurers who dared to look up to wonder and to reach. It's a slow, steady march into the future, a quiet unfolding of destiny that begins not with a bang, but with a whisper and the gentle hum of dreams taking flight. Well, curious minds and sleepy thinkers, that's all we have time for today. I hope you've enjoyed drifting through this quiet exploration of the colonization of Mars, allowing these grand ideas to gently settle in your mind, perhaps even sparking new dreams as you drift off to sleep. This journey has been a glimpse into the vast potential and the formidable challenges that await humanity among the stars. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics where we can continue to explore the mysteries of the universe together, always at a pace gentle enough not to disturb your peaceful repose. But for now, I'm Alex McCone, and this has been Astrum. All the best, and see you next time, perhaps under a different sky, or even one day on a different world.